Okay, so we're going to begin to look at sine waves and AC circuits. Circuits 2 is really about AC circuit analysis. So it's important that we begin to understand the critical thing in AC circuits, which is sine waves. The sources that we consider typically are not constant sources like you consider in circuits 1, but they are AC, meaning they're varying as a function of time. And the key waveform we use is the sinusoid. All right, so just to ground ourselves a little bit, let's kind of understand what we know to this point, or what we should know to this point, to what it is we're going to focus on really throughout the rest of the semester. So DC circuits, that's what you have learned in circuits 1, and we've continued with at the outset of circuits 2. Essentially what you're dealing with there, the most obvious form of these things is that you have a battery, a constant source of some form, driving some set of loads. And the simplest thing you could have is a situation where you have a battery like this and lamps. But it doesn't have to be that simple when you're dealing with DC circuits. The only critical thing is that you just have to have constant sources. And people think of that typically as just batteries, but that's not necessarily true. These days, to be honest, most systems that exist in the world really are DC. Best example of that is digital systems. Okay, so if I have inverters, for instance, so this is a digital circuit, right? So if I have two inverters cascaded on each other, in this particular case, I'll think about it like this. If I had a digital input, if I had a 0 here, I'd get a 1 here and then a 0 here. All right, so think of it that way. Typically, the way we would look at this is I would say that a 0 might correspond to 0 volts and a 1 might correspond to 5 volts. Now, the way that this circuit here would be implemented would be like this, okay? Now you're going to learn more about these particular types of devices or what I have in this particular circuit. But essentially, inverter A is this combination of RL and what I call a transistor. And then inverter B is this guy right here, which is RL and another transistor. Essentially, all the transistor is a switch. So I could actually think of it like this. I could think of the circuit as, and just to get ourselves a little bit comfortable here, this particular thing, this arrow, refers to a voltage source. So if I looked at what sort of a model for this little circuit, what it really looks like is this. I have a switch connected to ground, and then I have a resistor RL, and let me modify my switch a little bit, because what we typically say with a transistor, maybe it's not just a switch, but maybe it has a little bit of resistance when it's on, just the way it's drawn here. So this is that transistor. In other words, this thing here is the transistor. All it is a switch. And I have all of that connected to Vs, which is a 5-volt source. And Vn1 is basically the control signal that tells the switch to be on or off. Okay, so the way this guy sort of works is sort of shown here. So if we look at this time here vertically, so if time is on the x-axis here, if I look vertically, when Vn is equal to 5 volts, that's telling this switch over here to be on. Okay, so that guy is on. So if R on is really small, so close to 0, what that means is if this voltage is close to 0, I've got a voltage divider formed by Vs, RL, and R on. The voltage across R on is going to be really, really small, be close to 0. Okay, so this voltage here is what's called in that circuit V out 1. Okay, V out 1. So when Vs is 5 volts, this voltage here is going to be about 0. Okay, if I open the switch up, right? So when V in 1 is equal to 0 volts over here, the switch is open, and this voltage V out 1 would become 5 volts. Okay. Now I don't want to go through the full analysis of this thing, but essentially this is a DC circuit, right? All that this guy is right here, this sort of inverter, really is just a voltage divider. Okay. And I can make the model a little bit more complicated and add some capacitances and things like that. But even if I do add the capacitances, it's still a DC circuit. It's still a circuit that has resistances and capacitances. So because of how many computers there are in the world, there's a lot of DC circuits, okay? And obviously we don't just have batteries. So a more typical thing nowadays is that we have situations like this. And I drew a couple of different cases here, but typically I have a situation where there is some AC to DC conversion that happens, and then I have a DC bus. So I can have basically some sort of electronic system that I connect up to a grid that converts from AC, which we draw as a sine wave, to a constant source DC, okay? And then potentially, if I've got multiple different things I want to drive, I can have a DC to DC conversion. Inside of a computer, typically what you're going to have is, just your regular, laptop or something like that. You hook up to 120 volt, 60 hertz, and that gets converted eventually to several different voltages inside your computer, but may get converted down to 5 volts DC that powers the core digital stuff. Okay, so DC is really quite common, and so it is important for us to understand it. What I'm referring to here is kind of, in a modern context, people look at this quite a bit as the kind of thing I might have on board of a ship or on board of an electric vehicle, or even in systems now where we have renewable energy. Solar panels are DC, right? And so we have to typically have some sort of electronics that allow us to handle DC situations and to convert between AC and DC situations. So DC is actually quite common. But the power grid that exists is AC. All right, so I just wanted to keep that in mind, and we'll maybe talk about some of this stuff a little bit later when we talk about some applications. But wanted to bear in mind that DC is important, and DC is not just used for these kinds of silly, sort of trivial situations where I've got a battery and some lamps. All right, it's actually quite common in your digital electronics. All right, now the important thing to understand, just to ground ourselves in the definitions here, DC means constant, okay, direct current. AC means that our sources vary periodically as a function of time. And by definition, these sources have 0 average value, okay? So if I think of the simplest types of systems, all right, the simplest types of systems, if I have a DC source, all right, current flows that way, which means electrons are only moving in one direction. If I have an AC source, okay, what that means is, so sometimes the AC source I will designate like so. What that means is sometimes electrons are moving this way, sometimes they're moving that way. They're alternating back and forth, okay? The most typical type of AC waveform is the sine wave, which we're going to talk about here in a second, but this thing here is important. Sources have 0 average value in AC systems. We will talk later about situations where we have sources that have a constant value plus an AC value. All right, we'll talk about how to handle those. For now, we're going to focus simply on AC sources, which are sources that have 0 average value. Typically, they're sine waves, but they don't have to be. All right, as we'll learn, if we understand how to deal with sine waves, we can begin to understand how to deal with any type of periodic input. All right, part of the reason why we focus so heavily on sine waves is they're really common in our applications. All right, so many real signals that our circuits have to process are sinusoidal. All right, an audio signal, for instance. Okay, so if I have, my example here, if I have an A note, all right, that's a 440 hertz sine wave. Okay, we'll look at that a little bit in class to sort of understand that. But audio waveforms are sinusoidal. Okay, so when you're listening to music, there's basically sinusoidal waves that are hitting the air. You basically have a speaker vibrating the air at that particular frequency, and then it ultimately vibrates your eardrum at that particular frequency. So when you're processing audio, you're processing sinusoids. Typically, you're processing multiple sinusoids added together, but they're sine waves. Okay. Power waveforms are also sinusoidal. So in the power system, like if you go to the wall outlet, you get a voltage that is sinusoidal with a frequency of 60 hertz. All right. The generators that we designed to power the grid all output sinusoidal output voltages. And I talked briefly there. I mentioned solar panels. Solar panels are DC, but they're basically hooked up to electronics that make sure that what they put onto the grid is a 60 hertz sine wave. Radio waves that are transmitted over the air also have a sinusoidal form. So our radio circuits have to be able to deal with sine waves. So basically everything the most common types of things that we deal with in circuits, or that we have to build circuits for, usually audio, power, radio, typically are dealing with some sort of sinusoidal input. And so it's pretty common for us to have a need for understanding how to deal with these types of waveforms. All right, so because of that, we got to deal with a couple of things about the sine function, okay? And we should probably talk about both the sine and the cosine function. So what I've shown here is the sine function. So I really shouldn't say x of t here. I guess I should say x of theta, x m sine theta, like that. All right, by definition, sine is periodic in 2 pi radians or 360 degrees. And I should be really careful about that. Sine, if I use a calculator or most things, sine by definition is periodic in 2 pi radians, not really 360 degrees. For instance, in MATLAB, if I want to use the sine function, and I explicitly need to understand that this input is expected to be in radians. If I am entering something into degrees, I need to do a conversion, all right? So one thing to always remember is if I want to get to degrees or radians, so if I have something in degrees, an angle in degrees, so angle in degrees, always multiply by pi over 180 to get an angle in radians. Okay? Remember that MATLAB is going to make the assumption that sine, okay, is a function of an angle in radians. All right, so again, just wanted to understand this. If I look at sine, so at pi over 2 radians or 90 degrees, it reaches its maximum, right? Crosses through 0 at pi, has a negative maximum, 3 pi over 2, and then ends the period at 2 pi. All right, the amplitude is defined to be the peak value, x sub m. I could talk about the peak value of this guy, x sub m, or the peak to peak. All right, so in the lab, you may see that your oscilloscopes or your multimeters talk about peak to peak values. That would be 2 times xm for this particular waveform. Now, everything is defined in terms of an angle, but we don't typically use that. So I call this the sine function. What we really talk about are sine waves, which is to say that we have some sort of a function that is, or some sort of a waveform that's varying as a function of time. All right. So in other words, I have it as x of t, not x of theta. All right, and that x typically means that we're talking about a voltage or a current. Okay, and here, instead of saying theta, I say xm equals sine of theta, but theta equals omega t. xm sine omega t. In other words, what this means is that in a circuit, I have some sort of a voltage that's changing as a function of time. All right, so at whatever time corresponds to theta equal pi over 2. So in this case, pi over 2 equals omega t. Depending on what the frequency of the sine wave is, the voltage is at its peak value at a particular time. And there's some times when that voltage is 0. And there's some times when it's equal to its negative peak. And there's some times when it's back at 0 again. All right, so when we talk about an AC circuit, what we said is we have a source whose voltage is fluctuating as a function of time. Okay, and omega tells us how fast it's doing that. All right, so this guy is still a sine wave that is periodic in 2 pi radians. How quickly it varies depends on the frequency. So you see that there's two sort of key parameters here. All right, so there's ultimately 3 parameters that we'll think about, but essentially what I call the angular frequency, which tells us how fast this guy repeats, and that guy has a unit of radians per second. How quickly, how many radians is it changing per second? And then x sub m is the amplitude. Okay, so critical to remember that we're talking about voltages and currents, and those voltages and currents are changing as a function of time. All right. So a couple of things for us to sort of remember here when we're talking about these things. So we typically don't talk about omega as a frequency number. So I said that the voltage coming out of the wall outlet has a frequency of 60 hertz. Most people refer to frequencies in hertz. And we can relate that to what we actually have to plug into the sine function by saying that what we call the angular frequency in radians per second is equal to 2 pi times the frequency in hertz. All right, so frequency is hertz or 1 over seconds. Okay, so our definitions here at the bottom, angular frequency is radians per second, frequency in hertz. That all relates to the period. All right, so the period is the amount of time it takes for a wave to repeat. Okay, so when I say repeat, basically if I look at this value right here, or probably the better thing to do, typically what I do is I think about how long is it going to take to get from here, this peak, to this peak. Okay, that time is one period. So we say that these waveforms are periodic. All right, so for a sine wave or any wave that's periodic, if it repeats, all right, the value 1 period from now, if now is time little t, the value at 1 period from now, so t plus capital T, must be exactly the same. That's a periodic waveform. Okay, that's how I can determine that a waveform is periodic. All right, so the amount of time it takes for a wave to repeat is our period, and I can relate that to 1 over the frequency or 2 pi over the angular frequency. So you've got these 3 relationships here. Okay, so a couple of things that I want to see. So here's a waveform that we're going to take a look at. I want to before I move too quickly, I've talked here about the sine wave. The cosine wave is its cousin. We will use the terms, at least I will, almost interchangeably, cosine and sine. Cosine is actually the guy we like a little bit more. All right, so cosine looks like this. All right, it looks better than that, but that's my version of it. it starts out not at 0 but at a peak value, all right, and then varies as a function of time. So this would be pi over 2 here. This would be pi. This would be 3 pi over 2. And then he repeats again at 2 pi. Okay? So this would be as a function of theta. Now, in general, we try to relate all of the sinusoidal functions we have to cosine. And we're going to talk more about that. So in general, I refer to a waveform as some amplitude times cosine omega t plus phi. Okay? So there are 3 key parameters that define this waveform. One is this, the amplitude. One is this guy, the frequency. And one is this guy, the phase shift. So what they tell us, okay, the amplitude basically tells us how big the waveform is. Okay? The frequency, period or angular frequency, all of which are related to omega, tells us how fast the waveform varies. And phi is basically some sort of an offset, which tells us how far off we are from being truly just cosine omega t. So cosine omega t. Yikes. That was ugly. Cosine. How far off are we being from cosine omega t at t equal to 0? Okay? And that typically is measured in radians or degrees, right? Because cosine is a function of an angle. Okay? What I'm saying is more generally we have theta equals omega t plus some offset. And that offset tells us how far off we are from being just plain cosine. All right, so let's look at this waveform here and try to understand it. So just looking at this picture right here, all right, you should see in looking at this picture that x sub m, the amplitude, is 10 volts. Okay, so the peak value of this guy, which appears to occur, I don't know, whatever time this is right here. All right, that looks like it occurs maybe at 0.085 seconds, about that time. That's so apparently the peak value of this guy is x sub m. All right, so in this particular case, the way that I drew this waveform, I had a period of 0.1 seconds. So t equals 0.1 seconds. We said f equals 1 over t. So that gives me 10 hertz. And I said that omega then is 2 pi f, which puts this guy at 20 pi radians per second for his angular frequency. Almost never do we talk about angular frequency. All right, typically engineers talk in terms of hertz or period potentially. Okay, and you can look at this. I'll post these notes. You can see this, how I wrote the code here to make that plot. All right, what I want to do is say, okay, well, how do I look at this particular waveform and get some understanding? Let's say I was just told that I was given this waveform, given this picture, and I was told, okay, tell me what is x sub m. So we already said that's pretty obvious, that's 10, right? But tell me, what is omega equal to and what is phi equal to, okay? Well, to do that, first thing I would do is I would try to see if I could observe the period. So because this guy is periodic, we said that its value repeats after one period. So what I did here in MATLAB is I said, okay, let's look at when the peak value of this guy is 10, and let's look again at when the peak value of this guy is 10. And then let's look at how much time has passed. The x coordinate here is time. All right, so how much time has passed? So it appears that initially, at this time, it was 10 volts at about 0.0876 seconds. And here, it looks like it's peaking again at 10 at 0.1875 seconds. All right. So if I do the math there, so how much time elapses between 0.1875 and 0.0876, according to my math here, it's 0.0999999 seconds, and that's approximately 0.1, right? So I said it was 0.1, right? Over here I said I drew it for 0.1. So it probably should be 0.1. There's probably just some numeric accuracy in my measurement here. But if you look at my error between what I measured and what it actually is, that's certainly well less than 1% error. So I'm pretty close to being correct. But I can see from this that the wave repeats every 0.1 seconds, or at a rate f equals 1 over 0.1 of 10 hertz. 10 hertz. Okay. So I should be able to look at the waveform and identify these things. And you can begin to see, if I can identify the amplitude and the frequency and the phase, I can potentially simplify some analysis. This is really the reason why we're doing this. We'll continue to talk about this more over the next couple of days. Okay. So seeing the period and the frequency is not that hard. The part that's a little bit harder is figuring out, how do I see the phase shift? All right, so what I do is I look at this guy at t equal to 0. And at t equal to 0, I have that the value is 7.071. So I see that I have x of 0 equal to 7.071. Okay? And because in general I've said this thing is xm cosine omega t plus phi, okay, I'm going to plug in to this expression here. I'm going to plug in t equal to 0. So this thing becomes xm cosine 0 plus phi. Okay, so whatever I have at time t equal to 0 should be able to tell me what this phi is. How much off shift do I have from being a pure cosine? Okay, so if I do this, I know that xm is 10. All right, so 10 cosine phi. And if I solve that, I figure out that phi is equal to 45 degrees. Okay, 45 degrees. So that tells me that the total waveform is what I have written here, right? 10 is the amplitude, cosine 20 pi t, all right, plus 45 degrees. Now, the meaning of this positive phase shift, the question is, how do I know whether it's positive or negative? All right, well, the reason why it's positive in this particular case, the way I think about this is if I kept going, the waveform would look something like that. All right, it would look not as fat as what I just drew. It would go up faster. All right, so that's a terrible cosine wave. But that means that the peak value, which occurs somewhere over here, that peak value happened before t equal to 0. So because it happened before, what I had to do is I had to pull cosine effectively to the left. So if the peak happens before t equal to 0, all right, then it's a plus phase shift. If the peak had happened after t equal to 0, then we would have said it was a negative phase shift. Okay? All right, so we're going to use those terms a little bit as we go. We should begin to get familiar with when it would be positive and when it would be negative. Basically, you're saying if the waveform is pulled to the left, you add a plus sign. If the waveform had been pulled to the right, you would have added a minus sign. All right, so let's look at how these AC waveforms apply in static circuits. So what I've got is a circuit here in Simulink, and I have basically a source that I've connected, which is 10 volts cosine 2 pi 100t. So this guy has a frequency f equal to 100, or a period equal to 0.01 seconds. So he should repeat every 0.01 seconds. At least the source does, right? What I've got is a voltage divider, so it better be the case that V out is equal to 2 over 4 plus 2 times V in. Okay, so V out should also be a cosine wave, and the current in this circuit would be V in divided by 4 plus 2. All right, so that also better be a sine wave with a different amplitude. All right, so here's our analysis here. So the input voltage is the blue, all right, and we said it should repeat every 0.01. If I look at that, that's effectively what it does. And I should be careful. So one thing I guess I did that I didn't pay attention to when I drew this is this guy is actually a sine function and not a cosine function. So this is actually 10 sine, all right, omega t. All right, that's not all that particularly important. The critical thing is that V out is the voltage divider 2 over 2 plus 4. All right, if the amplitude of this guy is 10, all right, if I go through the analysis, 2 over 6 is 1/3. So the output voltage should have an amplitude of 10/3 or 3.33. And the output voltage, I see the peak value of it occurs where right at the same place where the peak value of this guy occurs. And that looks like it's about 3.33 as it should be. The current is here, all right, the yellow. What I see is, first of all, the critical thing I guess I should point out is that if you look at the timing of each of these waveforms, they're exactly the same. They have the same period, same phase shift, all of that stuff. All that's different is the amplitudes have changed. All right, so for the current has an amplitude of 1.667, right? Which if I do the math, the amplitude should have been, well, the amplitude of V in is 10, right? So divide that by 6 ohms, that's 5/3, or about 1.667, right? And you can see that's about where it is. So the only thing about these waveforms that changes is their amplitude. This is really important. The frequency and the phase do not change. So if I have a static circuit, in other words, a circuit that I would refer to as having just simply resistors, so no capacitors or inductors, all that changes is my amplitude. All right, so if I only have resistors, if I look at this, all right, here's the analysis we did on the full waveform. I could do a much simpler analysis. To be honest with you, I don't need to keep this cosine and sine stuff over here. I don't need that, right? I basically could say, well, what's the amplitude of the input? It's 10 volts. Well, the amplitude of the output, I just do analysis like I would in DC circuits, and I figure out that the amplitude of the output is 3.33, and then the amplitude of the current is 1.667 amps. If we then asked you, well, give us the true waveform, you would just say, well, I just take the waveform that's in the input and multiply that by whatever I found for the amplitude. That's my answer. In other words, I don't need to keep the whole time waveform around to do my analysis. When I do my analysis, I can just simply do it on the amplitude. Okay? Now that applies when I have only resistors. But what happens if I have R's, L's, and C's? So here's a slightly more complicated circuit. All right, so in this case, what I've got is cosine 2 pi ft is my input, and I'm actually going to play with f, okay, a little bit in this case. My resistor is 15.9 kilo ohms, and my capacitor is 1 microfarad. Okay, so that's my circuit. I can look at this guy and I can write my differential equation. So the capacitor voltage I have referred to as V out. All right. V in is this guy here, so it's got an amplitude of 1, and I'm going to change the frequency. So important to look at this. A differential equation is what tells me what the output voltage is. What we're going to find out is we can simplify things here a little bit. So with the differential equation, my solution always has two components, right? My transient component, so this guy, and my steady state. All right, now up until now, when we were dealing with DC sources only, this steady state value was always some constant. And the transient was always of the form AE to the negative t over tau. Okay? Remember, the transient solution solves the homogeneous differential equation, which would be, if I took this guy and said, what's the homogeneous differential equation? It would be dv out dt plus v out equals 0, like that. That would be our what we call our homogeneous differential equation. And the solution to this guy would be a e to the negative t over tau. Okay? I take that plus whatever my steady state solution is to figure out my v out. All right, so let's look at what that would look like. Okay? So if I ran this guy in simulation, or if I set it up in the lab, what I'd see is something like this. It's hard to see this, but there's a blue waveform, which is the input. All right, so I set my f to be 0.1 hertz. Okay, so if I look at this, early on, here's the transient solution, all right, as the capacitor, if it was initially uncharged, so if the capacitor voltage started at t equal to 0, here's the transient, and then basically for the rest of time, I see the steady state solution, which is to say that what the steady state solution is apparently cosine. Sorry about that. All right. What it says is that this guy is cosine omega t. So it appears that the steady state solution is also a cosine wave, and it's pretty close to the input voltage. Anytime I have a circuit with R's, L's, and C's, the steady state solution is also always going to be sinusoidal. Okay? And there's some common things that we need to understand about that. Important thing I see here is the transient solution is over relatively quickly, and then all I have is that steady state solution, and the steady state solution is itself also always a sine wave. Now if I increase the frequency, that starts to change. So in this case I upped it to 10 hertz. So I can still see that there's some impact of a transient initially, but the transient basically dies off pretty fast, and once I'm in steady state, the red here is clearly just also a cosine wave. Important thing to remember is that the cosine, my output, V out steady state, a little bit more obvious here, is some amplitude, some new amplitude, cosine omega t plus phi. Clearly the frequency of the red and the blue is the same. Right? They're repeating at the same rate, but they have different amplitudes and they have different phase shifts. Okay? That's kind of the important thing, is that there's a different amplitude and a different phase shift, but their timing is exactly the same. Okay? So here what I did was I zoomed out long after the transient was over, which is just, basically just to emphasize the fact that after that transient's over, it looks like I just have two sine waves, an input sine wave and an output sine wave. So typically, we don't really concern ourselves with the transient solution because the transient solution disappears pretty quickly. All right, think about this for a second. If I'm hooking up if I'm hooking up to a speaker and I'm listening to audio, so I'm playing a song, there's some transient when I first start playing that song, the transient's over with, and then I'm listening to the song for several minutes, so I'm basically sort of in steady state most of the time. So I really care about steady state analysis for most sort of signal processing applications. And so we're going to focus primarily right now not on the transients, but on what's happening in steady state. So in other words, we want to understand how the circuit affects this amplitude and how it affects this phase shift. All right, so here I do it at 1,000 hertz. So I increase the frequency of the input even higher. So the amplitude of the input is still the same. All right, it's an amplitude of 1 volt. But my steady state solution now, once I zoom in, is really, really small. All right, you should see that this guy is peaking. Hopefully you can see that right around here. All right. So he still has the same timing, but his amplitude is even smaller than it was before, and his phase shift is apparently even bigger. All right, so sort of summarizing what I see here, when I first did 0.1 hertz, my input voltage and the output voltage, the voltage across the capacitor, were basically the same. At 10 hertz, right, 10 hertz, so let's go back to 10 hertz, what I see is the capacitor voltage is smaller and phase shifted away. So initially they're about the same. Here I see that the capacitor voltage is smaller and phase shifted. At 1000 hertz, I see it's even smaller and phase shifted even more. All right. Okay. Important thing to note that the peak of that capacitor voltage is shifted to be a little bit later. All right. In other words, it happens at a later time. So this guy peaks at 14.1 seconds. This guy looks like he peaks at maybe 14.11 or 14.12 seconds. So the output voltage is shifted back a little bit. Okay. So if I wanted to measure that phase shift, all right, what I might want to do, so again, what we said is that the output, so V out steady state, is equal to some amplitude times cosine omega t plus phi. And we said the frequency, the input, and the output stay the same. All right, let's say what I wanted to do is I wanted to figure out at 10 hertz, what's the magnitude of V out, what's the amplitude of it, and what's the phase shift. All right, so what I'm showing here is this oscilloscope in Simulink, all right, for that circuit. So the yellow waveform here, the yellow is, this guy is V in, and the blue is V out. Okay, so what I do is I took my cursors and I tried to measure the peak value of that guy. So it appears that the peak value I got is 0.0744. And where I'm looking at that is it says right here, so for cursor 1, the value at cursor 1, which is apparently right there, is 0.7, well, it says 7.044 times 10 to the minus 1, or 0.7044. So that tells me that V out, the amplitude, is 0.7044 cosine 2 pi 10 t, and we still don't know what phi is, all right, but it's 0.7044 volts. Now what I want to do is I want to figure out what phi is. I want to figure out how much shift there is between the input, so the yellow and the blue. So basically how much time passes between here and there. How big is that gap? All right, so here I kind of zoomed in on it. All right, so what I did was I put cursor 1, all right, you can see cursor 1 right here at the peak value, or as close as I could to get it to the peak value of the yellow, the input. And I put the blue here, or cursor number 2 at the peak value of the blue one. So basically what is this delta t right here, right? How much time elapses, and I can relate that to an angle. So what I see is the cursors tell me how much of a delta t there is, right? 13.062 milliseconds. If I want to relate that to an angle, right? So remember we said that omega t is how we relate to angles. So if that time is 13.062 milliseconds, if I multiply that by how fast that waveform is changing, so in this case 2 pi 10, I get that this guy, if I do that math, it comes out to 0.8207 radians, or 47 degrees. So what I did there is I said 0.8207 radians times 180 over pi, and I got that to be 47 degrees. So in other words, what that tells me is that V out steady state is 0.7044, like I said before, times cosine 2 pi 10 t plus 47 degrees, like that. That's our true waveform. Okay, so we're going to learn a lot more about that, and I should be careful. It's actually minus 47 degrees. All right, it's minus 47 degrees because the peak of the blue happens later. In other words, I had to shift the yellow, my input, I had to shift it to the left. Sorry, I had to shift it to the right. It occurs, this peak occurs at a later time, all right? In other words, this peak occurs about 13 milliseconds after this peak. So in other words, I pulled this guy, I pulled the yellow, the input to the right to get it to have that same peak time, okay? So that's a negative phase shift, okay? So that's our output, all right? So I subtracted the 47 degrees because the capacitor voltage has its peak at a later time. Now, sort of our key takeaways from this, right? So if we have AC circuits with only resistors, only the amplitude of the input changes, okay? If I have AC circuits with R's, L's, and C's, there's going to be a transient, but that transient tends to end relatively quickly, and we don't concern ourselves with it too much. In steady state, what I saw is that both the amplitude and the phase angle change, but the frequency does not, okay? So omega or F do not change, okay? The change in amplitude and the phase do depend on the frequency of the input, though, all right? And that'll become something important. All right, so essentially we're going to use all this stuff to sort of simplify some analysis. Basically in AC circuits, we're typically interested in processing the input. All right, so the input is usually some sort of an audio signal, power signal, radio signal, something like that. Typically assume the transient dies away quickly, and we usually ignore it. All right, we're interested in processing that sine wave signal for minutes or hours, and so the transient isn't really much of a concern. So we typically talk about it as AC steady state. All right, so once the transients are gone. Basically, in this case, all the voltage and currents have the following, right? They all have the same frequency as the input source, and they have a different amplitude and phase than the input source. So what that tends us to imply is that in general, like if I only had resistors, I only have to track amplitudes. But if I have resistors and capacitors, I have to track amplitude and phase, okay? But we can use that to simplify our analysis. In other words, this kind of suggests that all we need to do is to track amplitude and phase. We don't actually have to track the whole waveform. All right, so we'll use that fact to simplify our analysis next time.